the third week of the Strength of Materials course. This week, we'll be seeing about bending, deflection, and torque. Last week, we learnt about principal stresses and Mohr's circle. We also saw a few problems that are related to principal stresses and Mohr's circle. The table of contents for this week would be a typical beam, supports, loads, beams, internal forces, bending, deflection, torsional deformation of a circular shaft, and torsional formula. The learning objectives for this session would be to learn about a typical beam and its uses. We'll also go through different types of loads and supports that a typical beam would have on it. Then we'll learn about shear force diagram and bending moment diagram with few plots. We'll also see problems related to it. We'll also go through important concepts like bending, deflection, and formulas related to it. Finally, we'll end this session with learning about torsion on a circular shaft, and we'll also see about torsional formula, and we'll work on a problem that is related with torsional formula. Now we look at a typical beam. A beam is a versatile structural element, that is, it can be used in many different areas. Beams primarily resist loads applied laterally to the beam's axis. The mode of deflection in beams is bending. Typical examples of beams are RCC buildings, steel trusses, and vehicle axles. If we can see in this figure, which is in the right side, as shown in this figure, the loads carried by a beam are generally transferred to columns, walls, or girders. These structural members, like columns, walls, or girders, then transfer these loads to adjacent structural members to equally distribute the received load. Next, let us look at parts of a typical beam. So what we see here is the front elevation of a beam. We can also call it as the front projection of a beam. This beam rests on two supports at both the ends. Because it is resting on two supports, it will create two support reactions, and these support reactions are termed as R1 and R2. The span of the beam is between these two supports, and this span can also be called as the total length of the beam, which is L. The longitudinal axis cuts the beam lengthwise. Same way, there is one more axis, which is the transverse axis that cuts through the cross-sectional area A dash. In the right side, we can see that the cross-sectional area is given as a rectangle. In this rectangle, there are two more elements. One is the breadth B and the height H. Now, our important variables to note for a beam are span L, breadth B, and height H. The next comes our weight. When we have a load acting on the longitudinal axis of a beam, which is along the transverse axis, this load can be represented as weight, which is W. For some information, the cross section of a beam historically used to be squares or rectangles and were made of stones. Nowadays, these are also made of metals and combination of wood and metal. Sometimes with advances in engineering, mechanics and processing methods, we have developed beams with different cross sections like H beams, I beams, L beams, T beams, and double T beams. These new and improved shapes have better load bearing capacities and also better stiffness. Next, let us look at support and support reactions. A structural support is a part of a structure or a structural membrane that provides necessary stiffness and strength in order to resist internal forces. These forces can be forces of gravity or lateral forces that can be caused by gush winds. Now, supports will help guide these loads safely to the nearby membranes that can be used to distribute these loads. A beam is subjected to vertical loads that needs to be transferred below. This is where supports come into play. So basically, supports offer stability and allow movements in some desirable directions. Also, supports can be used to connect elements with the beams. Next, we look at what are the common types of supports. The common types of supports are roller pinned, fixed, and simple supports. So, the first we'll be looking at is the roller support. In roller support, translation is allowed in one direction. Translation is the motion by which a body shifts from one point to another. For example, translation motion is the motion of a bullet fired from a gun. In roller supports, rotation is allowed. Thus, allowable movements in a roller support are horizontal movement and rotational movement. However, there is no movement in the vertical direction. Thus, the number of reactions is 1, which is in the vertical direction. Movement is restricted only in the vertical direction as we saw earlier. Thus, here we can see that we have one reaction which is RV in the vertical direction. Also, horizontal and rotational reactions are 0. Roller supports are commonly depicted as shown in the figure. Some examples of roller supports are rubber bearings, rockers, etc. The next type of support is a pin support. This is also known as hinged support. Pin support does not allow translation in any direction. That is, there is no movement in the horizontal or vertical direction. However, rotation of the beam is allowed. Thus, the allowable movement is only rotation while there is no vertical or horizontal movement. Thus, the number of reactions here are 2. One vertical component and one more is horizontal component. Some common examples of pin supports are bolts, pins, and connections and trusses. Another example of a pin support is the human elbow. If you can feel a human elbow, it can be extended and flexed or rotated, but you cannot move your forearm left to right, which is actually translation motion. However, a single pin support cannot completely restrain a structure, and at least 2 supports are needed to resist internal moments. The next type of support is fixed support. In this type of support, no translation motion or rotation motion is allowed. Thus, the beam cannot move along the horizontal axis or the vertical axis. It also cannot rotate. Because there is no allowable movement, it might be vertical, horizontal, or rotational. This kind of a support has 3 reactions. One is the vertical, which is RV, second is the horizontal, which is RH, and the third one is the moment, which is M. Fixed supports are generally seen in column to beam connections. They are also seen in cantilever beams, where having a single support is beneficial. Next, we look at loads. What is a load? A load is a force or acceleration that is applied to a structural or mechanical element. It will cause stress, which causes deformation and displacement on the object. In this figure, we can see a rope bridge as the person walks over it. So, by definition, it will bend or deform. And loads can be of 2 types. One is static and the other is dynamic loads. Static loads are constant over time, while dynamic loads are variable or moving loads. The other classification of loads is the spread. Spread of loads is the distribution of loads on the structural element. Few examples for all these loads can be given as for static loads, these are basically dead loads because they are not growing over time, but they are constant over time. And examples of dynamic loads would be live loads and environmental loads. When it comes to the spread of loads, which is basically how they are spread out on a structural element, the first type of load are concentrated loads. These act on relatively smaller area of the element. Thus, they are known as point load. Point loads are applied to a concentrated point on the support. An example would be a person standing at the free end of a diving board. Another common example is a motorcycle resting on the ground. The load of the motorcycle is distributed on 2 load points, that is each wheel. Now, these can be considered as point loads. Point loads are depicted using W, which is basically capital W, and the unit is kilonewtons. The next type of loads are Uniformly distributed loads. These are loads that are uniformly distributed over a large area of the element. In other words, the magnitude of the load will remain uniform throughout the whole element. One of the example of a uniformly distributed load is a wall that is sitting on a beam. For example, the wall here, its weight is evenly distributed over the beam under it. Another example is the self weight of a beam, which is uniform for a beam of even cross section throughout its span. In the left side image, if you can see, this is the beam and the self weight of the beam will fall over it and the load is distributed uniformly. Like how we saw earlier, the load is depicted as W and the unit is kilonewton per meter. The next type of spread load is called as uniformly varying load. In this, the magnitude of load will uniformly increase or decrease over the given area. Thus, it has zero intensity at one end and a fixed value at the other. This type of load is also known as a triangular load, as the shape of the load that is applied to this beam will now be triangular. Examples of uniformly varying loads are stairs and water pressure on a water tank. As we already saw, uniformly varying loads are depicted using triangles with one end having 0 and the other end having a magnitude of W, which is also represented using a unit kilonewton per meter. Uniformly distributed loads and uniformly varying loads are difficult to resolve when they are used in large systems. Thus, they are usually converted to point load. A point load is an equivalent load that is applied to a single point. This can be data mined by calculating the total load over the object's area and attributing the entire load to its center of gravity. For a uniformly distributed load, which is UDL, we will take the area of a load, that is load per meter or kilonewton per meter, and multiply it by the span of the load, which is L. The equivalent valid load, which is capital W, now acts at the center of gravity of the rectangular load. And this center of gravity will be at L by 2, which is half of the span. Similarly, the triangular uniformly varying load is the area of the load triangle, that is load per unit meter or kilonewton per meter multiplied by the span L multiplied by 1 by 2. We do this here because we know that area of triangle is half of length into height. Now we know that the length is the span, which is L, and here our height is W, small w. So here we take the area of the triangle, which is 1 by 2 into W into L. Thus, the equivalent load capital W will now act at the center of gravity of the triangle, which is L by 3 from the maximum value. Thus, for uniformly distributed load, which is UDL, W is the equivalent point load that acts in this center of gravity of the span L, which is at L by 2. Similarly, for UVL, which is the uniformly varying load, due to its triangular shape, the equivalent load W will be again acting in the center of gravity, which is L by 3 from the 0 position. Finally, let us look at beams. A beam is a structural element that is used in an engineering environment to provide a safe and efficient load path. These beams support the load by resisting beam bending under the load's pressure. We will look at the definition of a beam and how they are classified based on the type of a beam. We know that a beam is a structural element. It can be straight or curved. It can be homogeneous or composite. That is, it can be either made of the same material or a composite of two materials. Beam can have a constant cross section or be tapered. A simplified beam for ease of calculation is considered to be straight. Also, it is assumed that the deformation of the beam will be in linear elastic zone of the stress strain curve. We will also assume that any deflection due to loading will be small. One dimension of the beam is significantly larger than the other two dimensions. So here, span of the beam is larger than the breadth and height of the beam. By span we mean L, and breadth is B and H is height. Beams typically have loads that act in the transverse direction, that is perpendicular to the length of the beam. This load can be depicted using W. The beam is also supported at few different points. These points are called supports and are depicted using R, which are the reaction forces due to the support. Let us look at the types of beams based on their support conditions. The first type of beam is called a cantilever beam. These beams are fixed at one end and free at the other end. Examples of cantilever beam can be seen here in the right side image. In the right side image, there is a overhanging in this building. So this support is called as a cantilever support. The image on the left side shows us how a typical beam is shown as a free body diagram in a cantilever beam. As we saw earlier, there is one fixed end and one free end. The fixed end will have three reactions. So these three are the vertical reaction, horizontal reaction, and the moment. The free end will not have any reactionary forces as it is not restrained in any manner. The second type of beams are fixed beams. These are beams that are fixed at both ends. Since these beams are fixed on both ends, they will have two vertical reactions, two horizontal reactions, and two moment reactions. The next type of beams are simply supported beams. Simply supported beams are simply supported at both the ends. These two supports may be hinged, pinned, or roller types. An example of a simply supported beam can be a bridge girder that is resting on columns at two ends. Since there is only restriction in the vertical direction, two reactions are observed in simply supported beams. A vertical reaction force at each support.